do is let's just back up a little bit. I'm going to have some, need some volunteers later on. We're going to need some room to move. Awesome. We're all excited. So, today is a really, really important day at NASA. Today we are launching a mission called MMS. Okay? It's probably one of the coolest missions we've ever done. And we've done something else. It's also probably one of the most complicated ones. I think the majority of the hundreds and hundreds and hundreds of people who work on this mission don't actually really understand it. So now I'm here today talking to third grade, and later today I'm talking to fourth grade. I have to try to do this thing that NASA scientists, so the best scientists in the world, have trouble understanding. I hope they can explain it to a way that if I can understand it, I understand it at about a second grade level, so you all should be fine. So this is everything you ever wanted to know about NASA's MMS mission, but had no idea where to start. And that's me. Now I work at NASA Goddard Space Flight Center. So, Goddard Space Flight Center is right outside of Washington, D.C. Yes, I drive around this every day. Got 93 miles in the traffic. So this is an aerial shot of it. It's really big. We have about 10,000 employees. And we're the home of that. Have you seen this before?
Oh, yeah.
So I just say, what is it?
Satellite.
Yeah, that is the Hubble Space Telescope. So the coolest space images you've ever seen come from the Hubble. And we made that at Goddard Space Flight Center. This is about the size of a bus, okay? A regular school bus. This thing, which we're still working on, which it will hopefully launch in a couple of years, is called the James Webb Space Telescope. That is about the size of 3 tennis courts put together. So that one, the belief is that if it was on Earth and somebody lit a match on the other side of the moon, we'd be able to tell. That's how sensitive it is. And then we have some other satellites here. This one up here measures rain across the Earth. We do a lot of Earth science instruments. This one down here maps land. So a lot of those space maps that you see, like maps from satellite images, that's all there. This one was one that just went up about a month or two ago called Discover. It was actually originally built about 20 years ago, and then it was stored in a bag, and then we finally got it off. That investigates something called space weather. What can you talk about today? And this last one, you're going to see a lot of pictures of the sun in this presentation. A lot of those are taken by that. It's called SDO, the Solar Dynamics Observatory. So, that's another one. And every single one of these. And there's many more. So, enough about me. Okay, MMS Mission stands for Magnetospheric Multi-Scale Mission. So the S is in scale. It basically is going to be 4 spacecraft working together to provide 3-dimensional information of something called magnetic reconnection in the Earth's magnetosphere. It's complicated. So I think about it a little bit, and I'm like, that guy, I have no idea. When I start trying to think about it more, it becomes more like that. Oh, it kind of drives your brain a little crazy. So we're going to go all the way to the beginning. Have you talked about magnets?
Yeah.
So you have a North Pole and a South Pole. So if you put 2 magnets together, they're either going to do one of 2 things. They're either going to stick together, or they're going to push each other away. And that force that you feel is a magnetic force. So basically what's happening is that you have a magnetic field, which is, can you see magnets pushed together? Do you see like little hands stick out? No, it's an invisible field called magnetism. That's actually the flow of these things from one side to the other side, a lot like a battery. So you have a plus side and a minus side for a battery. Current flows between either pole of the battery, just like a magnet, because North Pole and South Pole, a plus or a minus. A battery has a plus or a minus. That can be used to power something like a light bulb. So magnetism, one thing we have to remember for all of this, magnetism and electricity are like the peanut butter and jelly of the universe. They go together. You can't have one without the other. Okay? Every time you have electricity going this way, it brings along all of its magnetic friends. Whenever you have a magnet There is electricity. They go together.
Oh.
Like peas and carrots, but chocolate and peanut butter. Or sun butter. Yeah, so, the Earth is a big magnet. That's why I have the North Pole and the South Pole. So the Earth acts like a big, solid bar magnet, just like that. But why is that? Because inside the Earth, we have the core. Who knows what magnets are usually made out of?
No.
And so the kind of metal that most magnets are made out of is called iron. The middle of the Earth is a giant iron core. It's huge, and it's right in the middle. Then outside of it, it's a little looser. It's stuff like magma and other things like that. So all of those interactions, everything flowing around the core of the Earth, starts creating this big magnetic field. So you can picture it kind of going from the North Pole to the South Pole along these lines. So we have a giant magnet in the middle of the Earth. So we have a magnetic North Pole and a magnetic South Pole. Just like that picture of the magnet, we're going to be getting these big magnetic fields surrounding the Earth. In a perfect world, if the Earth was just hanging out all by itself, nothing around it, these magnetic fields would make perfect little circles from the North Pole to the South Pole, South Pole to the North Pole, South Pole to the North Pole, all the way around. So you have this big magnetic field coming out from the sides, big magnetic field coming out from the other side, and see underneath where they all come in, it's kind of empty. Okay? You're going to remember that for later. So the Earth is a giant magnet. So, remember how I said if the Earth was hanging out all by itself, it would look just like that? Not so fast, son. So, a lot of people think of the sun as this happy little thing in the sky. Or maybe a cool thing in the sky. You know, that's what turns our grapes into raisins. However, the sun is a little, let's do everything. Because that's where you see it. And why is that? The sun's not this beautiful little yellow glowing thing in the sky. The sun is a giant ball of plasma. A giant ball of plasma. And it's violent, and it's scary. And there's lots of explosions and everything going all over the place. And since it's just a giant ball of plasma, there's no North Pole, there's no South Pole, there's holes going all over the place. Wait, whoa. What's plasma? So here's a picture of the sun taken by the Solar Dynamics Observatory. So you have all this stuff going all over the sun. Anybody know what this thing on the surface of the sun would be? Yes, it's a big explosion. It's called a solar flare or a coronal mass ejection. Those get huge. But let's back up again. So what's plasma? So, question. See if you know this one. Anybody know what the states of matter are? In the back.
Do you know what 3 kinds of matter there are? In Mr. Schweitzer's class, if anybody has a suggestion, wants to give it a try, anybody know what the 3 states of matter are? They're opening up. Let's let them have a turn too.
Anybody have an idea of one of those, at least one of the states of matter? We've talked about them with the snow. Gonna be shy today? Apparently we're going to be shy today.
Okay. Juliana, do you know what? Say it loud.
Solid, liquid, and gas. And in this case, we're looking at water because we have too much. So solid water would be ice. Liquid water would be water. And steam, the water vapor, would be the gas. So I bet all your teachers said there's 3 states of matter, right? Exactly. Do you know what the 4th one is?
My dad tells me all the time. It's like something like that's
Kind of. It is plasma. Yeah. So there are 4 states of matter. And which one do you think there's more in the universe? Solid, liquid, or gas? Just say it.
plasma.
set you up for that. Yes, plasma. Plasma makes up the majority of the mass of the universe. So, what are you talking about? So, let's just look at water for right now, because we all know water. So, we have an entire ocean of water. We can make that smaller by taking a glass of water. And out of that glass of water, we can have just a little drop of water. And we can break that water drop up into tiny little droplets of water. Well, if we go smaller and smaller and smaller and smaller and smaller and smaller and smaller, we end up getting a water molecule. Anybody hear water ever called H2O?
Yeah.
Okay, that's because in a water molecule, there are 2 hydrogen atoms and an oxygen atom all joined together. And they go around like they're like peanut butter and jelly. They stick together, and that arrangement of atoms makes a water molecule. But this is actually an oxygen atom and a hydrogen atom and a hydrogen atom. Hydrogen atoms are the most simple atoms in the universe. You have right here. In the middle, you have a proton, which is a plus. On the outside, you have going around it an electron, which is a minus. What happens when we have a plus and a minus together? Much like a magnet, that there is an attractive force. Like magnets want to stick together on opposite sides. Exactly, and that's what holds the atoms together. So, a helium, which on the periodic table of elements is number 2, it's 2 because you have 2 positive in the middle and 2 electrons. Now, I need 4 volunteers, 2 of which you don't mind holding hands.
Okay.
With each other. So I need 2 protons. I'll go with you 2 because you're right in the middle. So okay, stick this on your head. Stick this on your head. You are a proton. You are a proton. You 2 are hanging out in the nucleus in the middle. So now let's see.
And I don't know if you can tell Mr. Schweitzer's class, but they have little plus band headbands on.
Okay, so I need, let's go with you 2 right there. That's the 2 of you. Put on your head. So, okay, much like Ring Around the Rosie, these protons are tight together in something called a nucleus. You just hang out. The electrons are basically playing Ring Around the Rosie with you. So come around. You 2 hold on. You 2 go around them, but hold hands around them. Like this. Yes, go around them.
Just
Like
go
this.
around them.
You know, like a big
Circle.
big circle around them.
Cup hands.
Yeah, cup hands around them. Okay, so there is our atom. So, helium, come over here.
And
Helium atom, come over here. Everybody come over here. No, but you gotta stay attached. Nuclear forces say so. So now helium atom, come over here. These electrons are stuck with these guys because they're all bound together with atomic forces. Now, how do we turn these guys into plasma? Okay? Plasma is made when a whole lot of electricity and a whole lot of energy goes in here and basically makes them let go of their hands. Now, you just have a negative charge, 2 positive charges, and a negative charge, and they're not holding hands with each other. They still hang out, but you can kind of do what you want. Electrons, go over this way. Protons, go over there. Look, they're not together anymore. They broke their atomic forces, and now they're just free to do what they want. That's basically what plasma is. Thank you, Adams. Thank you very much. Thank you, thank you, thank you.
no longer
So that's how we make plasma. And so it happens that all over the place, air, anywhere, you have just atoms and molecules and electrons going on. But when there's enough energy, they break apart and turn into plasma. It's like basically a big soup. So, strong electromagnetic fields, so remember, electricity and magnetism are like peanut butter jelly. They basically create a field of plasma is a field. The particles can all hang out together, but they're not stuck together. Where have you guys seen plasma? What kind of sign? Like a neon sign?
No, she said on the sun.
Oh, on the sun. Yes, on the sun. I just gave away an answer. Let's see. What about lightning? How would you describe what lightning is? Lightning is, so ever smell it in the storm, how the air smells kind of weird?
It smells like electricity.
Exactly, because that's a whole bunch of these air molecules getting broken up, the atoms are getting broken up, and it's called ionized. Ion is anything with a charge, so either plus or minus. So you smell it, so you have all these loose ions floating around in the plasma, but then they reach ground, so they all get together and they short out. And they basically create a big spark because you have all these loose ions. So, where else have you seen plasma? I already gave that one, so I'll just say it. In a neon sign. So in a neon sign, you have a tube with a whole bunch of gas in there. When you turn it on, electricity goes through that gas and creates a plasma. And that plasma you can see because different gases will shine different colors. Now, a pair of scissors.
Oh, they're right on my desk, Mr. B.
I hope I can do this without shocking myself.
Huh? Oh, you. Oh.
So, you may have to adjust the camera for this one.
Do you need me to?
Don't kill your jealousy.
Okay, so, here we go.
So, Mr. Schweitzer's class, he has a light bulb and a pair of scissors.
And this is called a Van der Graaf generator. Handheld. What this is doing is creating an electric field. And I wish it was a little bit darker. I hope these work. As we see.
Oh, yeah.
So what we're doing here, this is creating a big electric field all over the place. All over here, we're basically creating a plasma. But much like lightning, we bring this together, we're creating a spark. 3. So, now just to give you some idea, if you take a regular light bulb like this, this is filled with the gas, and when an electric field is applied to it, it turns into plasma. Now it glows bright because they put this white coating inside of here, which makes it glow brighter, but that first glow that you get is essentially a plasma inside the stick.
Oh my God.
So you don't necessarily have to plug it in. All you need to do is bring the plasma into an electric field,
Whoa.
and it starts lighting up.
Oh, wow. Where'd you get that? I was with that. Magic. I was one of those. Me too.
So you don't even have to tap it, you just have to bring it into the field.
Where'd you buy this?
It's here.
This, yeah.
Mrs. Michelle,
Yes.
is there a way you can brighten up the room just a little bit? It's really dark for us.
Yeah, let's see. Ella, would you
I'll
turn?
turn on a light bulb.
Can you turn on the light, Ella?
It would.
If that works for us.
No, because it might.
Is that better, Mr. Schweitzer?
That's a little better. Our projector is kind of dim. That's a lot better from
Okay.
what we had.
Okay, so what we learned is that this plasma can be excited by an electrical field.
Wow.
I work at NASA. I get lots of things.
Let's go.
Anyways,
We are respectful.
So, what did we learn about plasma? Plasma is when regular atoms and molecules are exposed to a big electric field. And we showed it. So, You guys see this?
No, I don't.
So, here's a picture of the sun again. And here's a picture of one of those giant solar flares. If you see here, there's a lot going on with the sun. There's all these explosions going on, and see all this stuff coming out? That's basically because the sun is constantly throwing stuff out there. It's throwing out plasma all over the place, in all directions. The Earth sees that in something called solar wind. Because the sun is always blowing particles out, it's basically like wind on the Earth. So, these things are really, really, really big. Because the Earth, as big as it is to us, is actually really, really, really small. This just happened on March 5th this year, 6 days ago, 7 days ago, 7 days ago. There is an image of one of those big solar flares. Those big coronal mass ejections that shoot out of the sun and spray particles all over the universe. Not the universe, just our solar system. Right there is the Earth.
Whoa.
To scale. So, those could mess us up pretty good. But luckily we have that magnetic field. So, Mr. Magnetosphere shields up. How that protects us is that as all of these particles are flying at us, we have this big shield around us. So, for an example, this would be Earth, this tiny blue ball.
And that would be sun. Sucker ball would be sun.
Could I have a volunteer to hold the Earth?
Ellaby?
The Earth is in your hand.
Okay, so just pretending that this would be like one wave of solar wind. Here, hold that up. So if this just came flying through, it would just plow right through the Earth. But not, plow right through the Earth, and what would that do? There would be so much electricity on the planet, it would pretty much kill every single electronic device. No power, no computers, no Xboxes, no cell phones, no DSs, no iPods,
No, nothing.
no refrigerators. So it would be pretty bad. Now, luckily, we end up having this big shield around the Earth. So we're going to put the Earth in here. So now, the Earth is protected by this giant ball of magnetic fields. What's up? So now, when this big wave, the solar wind comes, it hits this shield, and instead of just destroying it, it goes around it, like that. So it blows past it, goes around the Earth, and comes down, and goes out here. This spot up here, and this spot up here, some really neat things happen. And that's kind of what MMS is looking at right now. Or will be. Thank you very much.
You did a good job, Ella.
So here's an example of basically what we just had. All the solar wind is blowing in from the sun. Sometimes it's just all the regular particles. Sometimes it's one of those big solar flares and blasting and hitting right to the Earth. It hits it like a force field, and it makes it go around it. But what happens there, two things. First of all, remember where I had that perfect little Earth with all the little field lines around it, and it was really nice and symmetric? But it starts getting smushed up here and gets dragged out in the back. And also remember how on the top of the Earth, all the lines came down into the poles, so they didn't have that force field there. That's one spot. So some of these solar wind particles come up and they hit the top and the bottom of the Earth. The rest of them get blown by. That creates sleeping beauties, also known as the aurora.
What's the sleeping beauty?
Oh, yeah.
Aurora.
What's that?
This phenomenon is called aurora. Where the solar winds come down, they can hit the Earth, and they on the North and South Poles, so like up around Alaska, they have these things called the northern lights, and these really beautiful skylights that go through. All different colors are dancing up there in the sky. That's because of these solar wind particles interacting and messing up the magnetic fields. So much like the plasma that we had with that purpley color from the air, all different stuff up there. That's what makes all the different colors. That's basically what's happening there. Yes, sir.
Would you get shocked if you touched
Probably.
it?
I'm thinking, well, it's a whole bunch of charged particles, so the chance.
Could you find
So it makes it really pretty. Now, it's not all pretty. Sometimes we have a big solar event, like a big flare shooting out, where sometimes the sun's more active than other times. Sometimes it's throwing out a little bit. Other times it's in a bad mood and throwing out a lot of stuff. But our magnetic field, it's always fighting it. It's always providing a good shield for us. So these solar storms can end up leaving the Earth basically being nailed with all those electronic particles. Not as much as if we didn't have a shield, but some stuff will still get by it. The bigger the storm, the more stuff that's going to, so the more that back end will be stretched, and the more stuff that's going to happen up here in this crazy zone. There's a crazy zone up here and a crazy zone back there. But this is why it's important. This is called space weather. Space weather, we don't have rain in space, we don't have snow in space. So what we end up having are all these solar winds, which create sometimes storms, which end up putting more and more electricity into the Earth. So what MMS is looking at is that region right in front of where the solar winds are beating up our force field here. And then remember when we had the soccer ball with that thing, it kind of came down to a tail. Where those things come together is another important spot that we're looking at. So those two areas and that whole thing where basically the sun's field and the Earth's fields are coming together and doing all the crazy stuff is what MMS is hoping to teach us. And I have like a 2-minute video in which some really, really smart people can kind of explain it a little bit of me.
Wait, turn on the lights. You can see it better.
I think so. Ms. Fuson, what do you think?
What?
We turn down the lights real quick.
Yep, we're gonna turn down the lights for the video. Can you see the video?
Uh-oh.
Uh-oh, not yet.
No, wrong way.
Look
Go
away.
away.
Go away.
There we go. Where's my cursor? Anybody see my cursor? There we go. Just do that. So.
The MMS mission is a mission consisting of 4 spacecraft, which will fly in close constellation to measure a process called magnetic reconnection.
The universe is full of plasma, and it's full of magnetic fields, and all over the place in the universe you have one plasma colliding with another. An example of that is the solar wind coming in and colliding with Earth's magnetosphere. And then the magnetic energy in the plasma, some fraction of that magnetic energy is converted very rapidly into plasma energy. So you can think of it as kind of like a magnetic explosion. And the reason this is important is because these explosions drive a lot of the weather patterns that we see in the magnetosphere. And so what space scientists like to refer to as space weather. And these space weather phenomena can have impact on our everyday lives. It can actually affect communication satellites, the power grid. So we'd really like to understand how these magnetic explosions work.
We need to measure reconnection in more than one location. We need to measure it in basically how it varies in space, how it varies in all 3 spatial dimensions. And that requires a tetrahedron. The additional fantastic benefit that provides is that it will actually enable us to recognize that we're looking with a reconnecting region much easier than a single spacecraft.
Okay, thank you, Franz. So, what they were saying there is that, so MMS is actually made up of 4 different spacecraft all working together. And those areas with the square, it's backwards. Go back to here. Oh. So the MMS mission is to go through and measure those regions there in 3D, because if you have this giant region of the area where all these magnetic explosions are happening, and you just have one little point, you're not going to get too much. If you have 2 little points, you have a line going through. If you have 3 points, you have a triangle, which, depending on how it is. But if you have 4, you have like a giant container, a giant space. And each of these spacecraft are going to be about 50 kilometers apart. That's pretty far. So it basically makes a big area where they can collect information and data with all these different instruments. So,
A kilometer is a little bit more than a half of a mile. And
okay, and this should be probably like one of our last confusing parts. So, when we talked about magnetic reconnection, we had the Earth's magnetic fields and the Sun's magnetic fields all coming together in those spots. What happens to make these little explosions, where you have one of those lines from the Earth and one of those lines from the Sun coming together, going in 2 different directions. And if you have magnets of 2 different sides, what happens if you hold a plus magnet and a minus magnet together, they want to get together. And there's that magnetic force here. And that's a lot just holding magnets in your hand. Imagine ones that go all the way around the Earth and deep into space. That's a lot of energy. So it happens that because they're going apart from each other and they want to kind of get a little bit closer, because they're going in 2 different ways and they like to attract, they kind of squeeze together. And then at one point, you actually shake hands. Okay? So the ones that are going this way, hello, how are you? And then the other ones go this way, how are you, sir? Once they get close enough, they can actually shake hands. At that point, you end up having the blue line from the Earth and the red line from the magnetic field from the Sun. They shake hands, and then guess what happens? Boom! I said it there. So you basically get a connection from the 2 different magnetic lines. So on this, it's kind of a demonstration of you have rubber bands. Remember, magnets hold a lot of energy. And what's the jelly to magnets peanut butter? Electricity. So, it's not probably good that I lost a pair of scissors. So, we basically have the Earth's lines here in blue going this way, the Sun's line going that way. When we bring them together, we're going to basically use these little binder clips here to kind of demonstrate how we bring them together for the handshake. Okay? So now these lines are brought together. When this reconnection happens, or the magnetic reconnection, there is a sudden and crazy cutting of the 2. So much like this, end up having, boom, they snap. It explodes a whole bunch of energy. And the energy that it explodes is plasma and other charged particles. And guess where it happens to go? You think it conveniently goes out into the universe? No, it goes right back to Earth. So starting to understand why we have to be able to predict and figure out when this stuff is going to happen so we can be prepared for it. So that's what this whole thing's about, finding the boom and measuring the boom and trying to understand the boom.
Everything's about the boom.
It is.
Yep.
Good.
Yeah, the TV remote.
Yeah, no, I use it. No, here, I just need you to tilt the. You just tilt it towards me a little bit. Just rotate it. Where's the little face? Somewhere there. There we go. So, a real quick overview of the. We should be good there.
Okay.
If it falls, I'm getting it. The MMS spacecraft, as I said, there are 4 different spacecraft to make that big 3-dimensional bucket. Okay? On each one of these are a ton of instruments, all to measure different things that happen out there in space. Some measure plasma, some measure ions, some measure charged particles, some measure electrical fields, measure a whole bunch of stuff. So you have all the instruments around here, and in the middle you end up having all the stuff which makes the spacecraft move. So the instruments were made all over the world, some in Sweden, some in Japan, some at NASA Goddard, some out in Texas, some in California, some all over the place. This one here, well, we didn't do. This one here is a little instrument that's part of an overall bigger instrument. There's 16 of these on every single spacecraft, and I was in charge of all the materials on them. So they take all, for each one of the spacecraft, they take all the instruments and they put them on what's called an instrument deck and go all the way around. Because these instruments all spin. So they spin, there's instruments, they can all take their samples. Meanwhile, while they're putting all the instruments on, they start building the spacecraft. Right here, we start with the bottom ring of the spacecraft, and then they start putting on the upper ring. Then they put all the stuff that keeps those rings together, which makes up the structure of the spacecraft. There, inside the middle of it, they put in all the propulsion, all the little rocket things which help get them into position, keep them spinning, moving them around. So that's all in there. Once the guts are in there, they put on the covers, and load it up. So that's just what we call the thrust tube. That's the middle of the spacecraft, which helps it go places. Yes, sir. It basically is a housing. So there it is, all cleaned up, ready to go into the clean room to get hooked up with that instrument deck. Yeah, it looks good. So now we put that middle part with the spacecraft onto the bottom part of the instrument deck. This is where they have all the electrical boxes, which tell it what to do. And all these people are in clean room suits. And this right here, the largest clean room in the world. What that means is that there is a ton of air filters. And good air filter sales make for a happy classroom. So there we are loading all the instruments up here.
Wow.
All the instruments around to the top. They lower it down with the crane. And then there it is, just about done. How's it going to get power? It gets power with solar rays. So all around the outside of it are these things which collect light and turn it into electricity to power everything. So there it is, one of 4 MMS spacecraft ready to go. Just to give you some idea, that's about 12 feet across. It's pretty big, probably from about the desk to
That's like 2 of you stacked on top.
about to here. Circle. So there it is. This is a whole bunch of senior people, but we have to stack them all on top of each other and do a lot of testing. So there they are at NASA Goddard, all stacked up, one on top of the other. That's a lot of stuff. So at that point, it gets all packed up and loaded onto a truck and sent down to Florida. So here they are from a couple days ago. They have all of them stacked up. They have the main rocket down there. And this is going into the capsule, which will be sitting on top of the rocket. Hold on 1 second, sir.